This first talk is from Ondřej. He's going to be talking about LPython. Very exciting. Thank you.
Thank you. Thanks for having me. This talk is about LPython, a novel, fast, retargetable Python compiler. Here is a list of authors. It's not all of them, but at least I tried to put everybody who contributed many big features. Brian Beckman, he used to be my boss at my previous company, GSI Technology, whose idea was that we should develop LPython. And then most of the other ones are students or former students, and all great developers, compiler developers. And I recently joined Microsoft. So motivation, why LPython? Well, my motivation is I would like it to fix all the issues I have with Python. Okay, so what issues with Python? Slow import time, things I don't like that I would like to see fixed. Slow import time, slow runtime, meaning low performance, packaging and distribution, custom hardware support, GPUs, and at both Microsoft and previous company, custom hardware NPU, neural processing unit. And I like to have good compiler error messages. So as probably all of you know, the usual error you get in Python is that the none type has no method append. And a compiler can take care of that. You'll never see this error from LPython. So can we write a compiler that compiles fast and generates fast code? That has to be part of the solution. So in LPython, it's kind of small. I'll show you a demo in a minute so you can see. We'll talk about all the details. But on the left, you see a code that we wrote in LPython, compiled, and show some examples. Some runtime execution. Oops. Some runtime execution time on the right. And we wrote the same thing in C++ using standard library, I believe unordered a map. And as in this particular example, you can see that we are capable of even running faster than the most optimized C++. Okay, so let's show you a demo. And before we go to the demo, let me at least briefly show you kind of the structure of the compiler. So it's kind of hard to see, but there are three front ends: LPython, LFortran, and LC. So LPython is what I'll mostly be showing you here. That's the Python front end. LFortran is a Fortran front end. I'll show you just a little bit of it. LC is a C++ front end, subset of C++. All three of these front ends parse the source code to AST, abstract syntax tree. The AST is syntax dependent, so different AST for Python, different for Fortran, different for C++. But after that, they all go to our internal representation, intermediate representation. We call it abstract semantic representation, ASR. And then we do many ASR to ASR passes, optimizations, lowering. And then we have lots of backends on the right. So LLVM is our most advanced backend. We also have a WebAssembly backend. I'll show you a demo. It runs in the browser directly, bypasses LLVM. The LLVM itself also has a WebAssembly backend. We can also use that. I'll also show you a demo. We have a prototype, just direct x86 generation, both directly as well as through WebAssembly. We can talk about it later why. And then we have what I call high-level backends. So we can generate C, C++ code, Python code, Fortran code, and Julia code. So from any of the three front ends, once it gets to ASR, we can generate all these things. Okay, so let's do a demo. And I'll want to show you, kind of give you a good overview of what LPython and LFortran can do. And then I will get back to the presentation. So I have, let's clean this up. Okay, so I have a simple, let's start with very simple demo first. So here is the most simplest Python code you can write. It's computing some expression. I'll move it up a little bit. Printing it, and so on. So let's compile with Python. So you launch it just like you would Python, but you put L in front. So compiles it, runs it. That's probably not what we could expect. We can run it with Python too. So the first lesson is anything that LPython can compile is a subset of Python, and so we guarantee it will run in CPython unmodified. If it doesn't, so if you compile something with LPython and it does not run in CPython, it's a bug that we have to fix. So let's look at what LPython did. So it's a compiler, so we can tell it. So if you just call it like Python, it generates a binary and runs it for you automatically. So it behaves like Python. The binary that it generated in this case has a default name, expert.out. When we examine the binary, I'll move it up a little bit. As you can see, it does not depend on Python. It's just it links our LPython runtime because we have some runtime utilities we have to use, but it does not depend on CPython. It's just a regular compiled code, has nothing to do with Python. In fact, LPython, the compiler, has nothing to do with Python. It does not use Python. We have our own parser for all of Python, our own AST. The compiler is implemented in C++, and when it compiles, it just generates lean, small, fast binaries. If we look at the size of it, it should be very small. Yeah, 16 kilobytes. Okay, now let's look at, so when we compile the code, so let's look at the ASR that it generates, because that is at the core of the compilers. My terminal is kind of big here, so it might be a little bit hard to read, but it's in memory, it's just a lot of structs, very fast implementation, so that it compiles fast. But when I print it in this Lisp-like or Clojure-like syntax. And you can see we represent every operation directly in ASR. And unlike most other compilers, the representation that we have, it does not lose any semantic information. So everything that's in the surface language, whether it's Python, subset of C++, or Fortran, we represent faithfully and exactly in ASR, meaning we can then generate the original code back. The things we do not represent is obviously syntax differences between the languages, as well as things that semantically do not matter. For example, it depends on the details, but like where things are imported, how things are declared exactly, and so forth. Okay, let's do some more advanced demos. So let's look at this expand demo. So, I like SciPy, and so we of course implemented SciPy support in LPython. So when we call this example with LPython, we'll get error messages because we have to enable a backend, which we don't enable SimEngine by default. And then we get something beautiful. So we get an error message, and then when we call it with Python, same thing with Python, we get the same error message. So in Python, the error message happens during the interpretation of how, when Python is interpreting, it's expecting for me to provide an argument, which I'll provide in a minute. And in LPython, that error message happens at runtime. In the compiled binary, we do a bounce checking and give the error message. So when we call the compiled binary with some number, let's say 3. So let's look at the code so that you can see what I'm executing. Here's the Python code. In this case, you can see I'm reading the first argument that I passed to it. I convert it to a symbolic expression. I compute some symbolic sum, or I guess a power, and I expand it. So when we run it with Python and SciPy, and now let's give it the number. Let's say 3. So this runs through CPython and SciPy, expands it and everything. If I run the compiled binary with the same exponent, it gives me the same result. You can see the ordering of terms is slightly different because we use SimEngine on the back end. And we understand the subset of SciPy exactly. And it goes through the compiler. It's represented faithfully in ASR. And so the ASR is independent of SciPy. LPython happens to understand SciPy. And ASR is completely independent, and then we can choose to implement it any way we like. We currently use SimEngine to do that. And now let's look at the speed of compilation. So let's say if I want to run the example from through SciPy, let's use some small exponent just to the time that you can see here is the time it takes Python to import SciPy and run this. Running it is relatively fast, but importing takes a long time. And then when we do the same thing, I have to do it kind of a two-step process here. I'll tell it to create a binary here, and then we'll run the binary with the same exponent. I think it was then. If we type, and I have to enable the backend, because we have to link sim engine, so we don't do it by default. So let's do it one more time. So in Python, it takes 0.4 second or 0.5 almost. And with LPython, compiling it and running it is faster than CPython can do all this. Okay. And now let's do an example in Jupyter. Hopefully it runs. Okay, I think it's this one. So I think I have an example notebook here. So this is very new. We just got this working on Monday, but it runs in Jupyter. It looks like Python. It is Python. Compiles as you would expect. Yeah. Let me restart it and clear the output. Let's see if I can zoom in. Is it better? Awesome. Yeah, so I'll just execute it one more time. So we can declare functions and call them. We use data class decorator to create structs. So this is effectively an equivalent of a C struct. So it's very, very fast and so forth. Yeah, so that works. And I think that's, I'm happy to answer questions at the end. I can show you a lot more. I'll show you at least one demo for the WebAssembly stuff. I think it's in here. So the LPython compiler itself compiles to WebAssembly through mscripten. It runs in the browser. Here is a demo. If you go to dev.lpython.org, I'll just refresh the page. My laptop is kind of slow. On the Mac, it's almost immediate. On the slower laptop, it's still pretty fast. So on the left, you can see some non-trivial, in this case, Mandelbrot computation in LPython. And then we compile to WebAssembly through our direct WebAssembly backend, and then we run the generated WebAssembly. If I change the color so you can see, kind of judge how fast it is. It's still kind of slow. It's slower for some reason than L4tran, which I have a demo here. If I refresh this page, I'm not sure exactly why it's slower. It should be equivalent, but here if I run it slightly faster. Okay. So that's WebAssembly demo, and then I wanted to show you a few more things from the internals of the compiler, and then I'll continue with the presentation. So I have to make it a little bit bigger. Okay, should be. So let's go to this examples directory, and then so now with L4tran, so we have a similar example that we started with Python. Now it's just Fortran syntax. When I compile with L4tran, so it will behave the same way. Now we can start looking at the internal representation. Again, if you remember what you saw from LPython, this is exactly the same identical ASR for all these expressions. And then if we start modifying the code and see what the compiler is doing. So for example, instead of printing sign, we can just, we have to cast it in Fortran to real, and we'll just print a sign, let's say. I'll just show you the result. Fine, so it prints a sign. And now let's use arrays. Let's kind of investigate what the compiler is doing with the array. So I'll make X an array. In Fortran, you can assign to an array. It's like in NumPy, it just becomes vectorized. And then the sign, now it's accepting an array. So let's compile it. Okay, so we get an array back. And now we can look at the intermediate representation. It's kind of hard to see in a terminal, but you can see one thing, and that is the compiler is representing the sign directly in the intermediate language, ASR, and it's accepting the array as an argument. So the type is an array. And then the compiler is applying transformations on it. And it's only committing to the final choices later in the pipeline. And so that allows the compiler to as the door is open to maximum performance. Because let's say somebody figures out, oh, there's a better way to compile a particular feature. In L4tran and LPython, the initial ASR does not do any lowering. It does not commit to any choice how you will implement, how the compiler will compile things. So we can add more passes later as needed. And the same with symbolics, works in exactly the same way. It parses SciPy to ASR. It exactly represents the symbolic operations. and commit, and then we have an ASR to ASR pass that transforms it to use SimEngine in this particular case. Cool. And then, of course, L-Fortran, just like LPython, runs interactively, so you can declare variables and assign to them and so on. It runs in the Jupyter Notebook too. I think last demo I want to show you is if you have some, let me make it a little bit bigger, some code in LPython, L-Fortran, and you compile through LLVM with all the optimizations you want. At the end, you can do a WebAssembly backend from LLVM and then compile everything to a web page and host it. So here is a demo that somebody else created in Fortran. So it's using Fortran to do the inference. And it's in this blog post. And we just took his code, discovered some bugs, we fixed those, compiled with L-Fortran, and hosted exactly everything he's done, we are doing as well. He used Flang. He had to also patch Flang, to be fair. So I think we are not that far behind. And then we compile and run. Okay. Let's get back to the presentation. Okay, so we've done the demo. So I talked about the architecture. Hopefully from this demo you kind of get a little bit of an idea how the compiler works inside. What I didn't show you, but I'm happy to show you after the talk, the compiler can, when it does the ASR passes, it can print those passes as the surface language, let's say Fortran or Python. So you as a user can see what the compiler is doing with your code as Python code, let's say, or Fortran code, step by step, how it's unfolding the arrays, how it's inlining them, whatever transformation is doing, you can see it. So if your code doesn't run fast, you can investigate what the compiler is doing with your code. It's not a black box, it's very open. Okay, we have, if you want to call LPython from just a regular CPython, so you have a big application, you want to hook LPython to call it, kind of like Numba. You can call the LPython decorator, and it works very similar to Numba. So it takes your function, calls LPython to compile it, and then creates an extension module, loads it in, and runs it. My favorite way to call into Python is the other way around, having the main program in LPython so that you can use LPython to generate a binary, and then call into CPython. So we have a Python Python call decorator on the left, and it calls. You provided an interface. You have to tell it which module it's in this case util. You can see it on the right. So on the right, I'm calling matplotlib to do some plotting, let's say. And on the left, I'm calling that function plot graph, and I give it numpy arrays. Well, they become numpy arrays in CPython. In our case, it's just arrays. And then we call, you can see the plot graph function being called at the bottom. LPython internally, it doesn't use numpy. It has arrays in ASR directly. So it's not a numpy array. And what LPython does, it creates the numpy descriptor when it's calling the plot graph function. So it knows you are calling into Python, so it will convert the arrays. We have about 4 different ways to represent arrays in ASR, depending on the array kind, either with a pointer or a descriptor or multiple ways. And numpy descriptor is one of them as well, so we can convert to it. Here is another example benchmark. I can see it's unreadable. On the left, what's in there is there are 2 functions, one in LPython, one in this case, Numba. It does a list benchmark. It computes, I think it's sorting a list. It's exactly the same code running in both compilers. And on the right, we can see compilation time and execution time. It's also a little bit small. The compilation time Numba on this particular example is a little bit faster, except on, I guess, Linux, where it's about the same. And the execution time on this particular example, when we ran it, LPython is a little bit faster. But I wanted to do more benchmarks. Problem with benchmarks is that ultimately any compiler, anything can be done in any compiler, and any compiler you can kind of eventually make to agree. But it's a nice example. You can make your own and test it both, and let me know how things go. So the front ends, we have 3 front ends: LPython, L-Fortran, and LC. LPython is a strict subset of CPython. So if it runs with LPython, it will run with CPython. And the only thing we require is types. We require types, and we restrict some of the Python dynamic features. And you always get a beautiful compiler error message. And I want to stress that if you don't like the error messages, report a bug. There is a link at the bottom of the error message. Just click on it on GitHub and post the error message and tell us what it should really say. And regarding the goal, LPython, I think of it as it needs to compete with C and Fortran, so it needs to be at least as fast as C, ideally better if we can. Fortran is a superset of Fortran, so there our goal is to compile all Fortran code eventually and running it interactively. And LC is a subset of C++. We currently use Clang AST to do the parsing, and then we translate Clang AST to our ASR. And we have the same deal. If LC compiles it and it runs, it needs to run with Clang and GCC. So the ASR is an abstract semantic representation. That's our main IR, intermediate representation in the compiler. As you have seen, it's independent of the front ends and back ends. The idea is to be as high level as possible. So the front end parses to AST and then it raises to ASR. It needs to be faithful to the surface language, meaning we do not lose any semantic information. We do not do any lowering. We represent every feature from the language faithfully in ASR. And the ASR itself is actually very small. It's only about 300 nodes, and that covers all of Fortran, and as it turns out, large subset of Python and C++. And so it's very easy to deal with. And it's very easy for newcomers to come in and start contributing. And then we do ASR to ASR passes. Here are some details. All of the L compilers, all the front ends are implemented in C++. They compile in about 30 seconds on a Mac laptop. On this laptop, about 2 minutes. But still, it's very fast. If you have experience compiling any compiler in C++, it takes a long time usually. It's only 30 seconds. And then we want the compiler itself to compile as quickly as possible, so that if you use it as a replacement to CPython or in Fortran as a compiler that you use every day, my goal is it needs to compile it just immediately. It needs to feel immediate, very fast in debug mode. In release mode, we want very fast runtime. Okay, we've seen the demos. And so here are tenets. We don't want to be never slower than C. If you discover any C code equivalent or C++ code or Fortran code that's faster with other compilers, let us know. Agile development is very easy to fix bugs. And consequently, from the design, we run on a very low budget. We have a small team, 5 to 10 people, contractors, mostly students. It's very easy to learn and contribute. It's easy to retarget. It takes 2 weeks to 2 months to write a new backend, as well as a new front end. For example, the C++ front end we wrote in about 2 months. It's very fast. We want to run interactively and compile to binaries. And our roadmap, we have a clear, focused roadmap. With Fortran, we just want to compile all Fortran codes. We are still alpha stage. All compilers are alpha stage, meaning they're expected to break if you use them. But we are pretty close to beta, and beta means it will not break when you use it. Okay, conclusions. So compilers, fast to compile, fast to run. That's what I want you to remember. Thank you.
Thank you, Ondřej. Yes, we'll take questions in the audience, and then for those remote participants, please post in Slack, and we'll read your questions out loud.
You were interfacing with SimEngine, which is C++, right? So
yeah.
How do I interface my libraries with an arbitrary C++ code?
Yeah, you have, I haven't shown it. We have, just like we have Python call to call into CPython, we have C call. So you can call into any C. Right now, C mostly, we support C. So if you have a C++ library, you have to write the C interface, and then you call it.
Have you tried compiling NumPy with it, or SciPy, pandas, and how close are you to making that work?
Yeah, I think best thing is to look at a demo here. So if I go, I'll kill this Jupyter notebook, and I'll go to our integration test. Let's take elemental 01 test. So here is an example of NumPy using some array operations, using NumPy signs, gives you an idea. As you can see, some array operations and and so forth. So this all should just work. Yeah, it works. It's a test, so it doesn't print anything, but that means that everything passes. And you can benchmark it through Python and LPython. So LPython can compile this NumPy and run it faster than CPython can do it with NumPy.
Okay, I'm going to come back to you, Andy, just to give other people time, and then you will get a question, don't worry.
Ondřej, I assume he has some particular application for this LPython. What is that?
The application is to fix Python. Now the actual application of my previous company was to program their custom hardware. They have a kind of NPU or customized hardware which is possible to program from C, but the company wanted to program it from Python because people like Python and NumPy arrays and be able to program it directly. But to do that, you have to have a compiler where you can write customized. It's a very custom hardware that requires special optimizations and special way of programming it. Very complicated. So it required a compiler that's easy to write these special optimizations and a backend for this custom hardware. So it was a good fit.
I still like the roast, Ondřej. That was good.
A question, how do you handle exceptions in ASR?
We don't have exceptions.
So
it's a good question. It's a good question. We could implement them. Right now we did not. Fortran, fortunately, also doesn't have exceptions, so that kind of takes care of it. It's a philosophical debate whether it's actually a good idea to support it or not. I have not. Haven't made up my mind. But if we do want to support them, we would have to add nodes and all the exception semantics and all the issues.
Yeah, they make us crazy. I was just curious.
Yes.
Okay, please raise your hands if you do have questions so I can make sure I go around the room.
How do I distribute my LPython code?
Yeah, you compile it to a binary and you give somebody the binary. And we do support just a static binary with no linking to shared libraries, so you just give it to somebody. Or, good question. I haven't mentioned that. It's a subset of Python, so you just use SciPy. You distribute your application on PyPy. You do pip install into your conda environment and tell LPython, here is my conda prefix, I think it's called, Python path, and LPython will find that application and compile it. So then, of course, users would have to have that installed. So I would think of it like that's a development machine where you have conda installed and you can actually compile it, and then you distribute just the binary. But if you don't want to, you can distribute the source code as well. And you just conda install LPython.
So what is the threading model, and are you free or not locked?
So the only threads we currently support is through OpenMP loop parallelization. So we have a parallel loop in ASR. And currently it's only hooked in L-Fortran, but we'll expose it in LPython soon. So in L-Fortran, you can parallel loops get raised to ASR, and then as usual, we represent the loops as a parallel construct directly in ASR. And then on the backend, currently we only support one backend for that, which is OpenMP, and we use OpenMP to parallelize. And so we have an ASR pass that transforms the parallel loop into a function and the API that, in our case, LLVM OpenMP implementation expects, and then we call it.
You mentioned a lot about you want to add GPU and NPU support within LPython. Do you have any because is it currently supported? If not,
So at my previous company, we had an internal branch that had that support for the custom hardware. For GPU, currently we didn't get to it yet, but we are close. I have some collaborators at AMD, so we are looking at. They're interested in, and we are interested, of course, to support it. Most likely, for the AMD use case, we'll use MLIR because they have an MLIR-based tool chain, and I think they support the OpenMP dialect in MLIR. So we are working on generating MLIR for just that function that you want to offload, and then piggyback on their compiler tool chain.
Okay, this is our last question. If you have questions that you want to ask our speaker, please go on to Slack, and he can answer some there. I'm just volunteering you to do that,
Excellent.
Andre.
I noticed you asked for annotations on the NumPy. That's a bit of a problem. So I assume those are specific annotations like integer and so on that really make sense.
Yeah, so our annotation, you see it right here. It's our own annotation because we have to specify not just the rank, but also an expression for the length. Or if it's allocatable, in other words, you allocate it at runtime, we have a notation for that too. So it's more specific than so far what I've seen with the official NumPy annotation is not as specific as we need. So we currently have our own. But if NumPy eventually settles on some annotations, even if they only work in a subset of what we support, we can extend LPython to support them. And you would only use these more specific ones when the NumPy annotation doesn't work.
Okay, let's thank our speaker one more time.